Imagine opening your editor, typing the word auto, the letter X, and a single integer inside curly braces.
Right, just explicitly handing the compiler the number 3.
Exactly. You hit compile,
Yeah.
fully expecting an integer, right? I mean, obviously. But the C++ compiler doesn't give you an integer.
No, it really doesn't.
It turns that single digit into an entire container, like a standard initializer list containing exactly one item. You asked for an apple, and the language handed you back a fruit basket containing one apple.
Which is just wildly frustrating when you first encounter it.
Okay, let's unpack this. We are taking a deep dive into the 20-year evolution of C++ auto-type deduction today.
Yeah, drawing from sources that trace this all the way from the early days of C++11 right up to C++20 concepts.
Right. And our mission today is to understand the 4 entirely distinct deduction rule sets hiding behind that one simple syntax.
So you can, hopefully start pulling your hair out over silent production bugs.
Exactly. But we have to start with that initializer list bug, because it is genuinely one of the most infamous quirks in modern C++ history.
It absolutely is. And what's really fascinating here is the why behind that decision.
Because they didn't just do it to be mean.
I know. The C++ committee didn't just stumble into this behavior by accident. They were attempting something highly ambitious. They wanted to unify brace initialization syntax across all possible contexts.
But curly braces mean the same thing everywhere.
Exactly, whether you're initializing a struct, an array, or just a primitive type. So when the auto keyword encountered a braced init list, the compiler's internal rulebook said, well, match this to standard initializer list by design.
They prioritized this grand vision of syntactic consistency over, the developer's entirely reasonable expectation that direct initialization of a single value gives you that value's type.
And they really did.
But it was so wildly counterintuitive that they actually had to go back and fix it, right?
They did.
And the sources highlight that they didn't just fix it in a new version going forward. They actually issued a retroactive patch to the standard.
Precisely. The ISO C++ committee issued a document, I think it was known as N3922, which was formally adopted into C++17. But uniquely, it was applied as a retroactive behavioral change to an already ratified standard.
That's just wild to me.
Yeah, to fix the issue, they fundamentally separated direct list initialization, which is just curly braces without an equal sign, from copy list initialization.
So after this fix went live, writing AutoX with braces finally deduces to a simple integer.
Right, while writing AutoX equals braces still gives you the initializer list.
I have to be honest, retroactively changing a ratified language standard that is not a patch. That is a massive admission that the original design was horribly wrong.
It is a huge deal, yeah.
It's like a home builder finishing a house, handing you the keys, and then a year later knocking on your door to admit they poured the foundation upside down and need to come jack up the house to fix it.
That's a great analogy. It's extraordinarily rare in systems programming languages. And it highlights a fundamental tension in language design that, we'll see repeated throughout this entire evolution.
Internal consistency isn't enough.
Exactly. Internal consistency is not sufficient on its own. Correctness against the developer's mental model is strictly required.
Right. If a language behaves perfectly consistently, according to its own logic, but violently violates the basic intuition of the human writing the code, the language is broken.
Could not have said it better myself.
So if the committee had to issue a retroactive apology for that specific curly brace syntax, it naturally leads to the bigger question. What else in C++ type deduction works completely differently than we developers assume?
Oh, quite a bit, actually.
Because this one failure with the braces points to a much broader problem you highlighted from our sources. You actually cannot design just one single operator for type deduction.
Exactly. If we connect this to the bigger picture, the real reason we have both auto and decltype as separate, distinct operators today is that you simply cannot design a single keyword that satisfies the two primary use cases developers need.
Which goes all the way back to Proposal and 1984 and 2006, right?
Yes, exactly.
Okay, let's break those two use cases down for the listener. Because coming from other languages, you might wonder, well, why couldn't C++ just make a single type of operator like everyone else does?
Right, so let's imagine we actually implemented a reference-preserving type of operator.
Okay.
If you write an A, and then on the next line you write type of A space B equals A, we have to look at what A actually is.
Which is just an integer.
Yes, but because A has a stable memory address, what the standard calls an L value, a strictly reference-preserving operator would return int reference.
Oh, I see.
Therefore, B wouldn't be a new integer, it would be a reference pointing back to A.
Wait, but A was declared as a plain integer. If I query its type to make a new independent variable, I expect a new plain integer.
Right.
I want a standalone copy, not a secret reference tying the two variables together. That sounds like a nightmare.
And that's exactly the problem. That mismatch between the visually declared type and the queried type was deemed way too confusing for everyday variable declaration.
Can see why.
Variable declaration almost always needs what we call reference dropping behavior. But if you make the operator drop references across the board, you completely break the second major use case.
Which is generic forwarding.
Exactly. Generic forwarding.
Walk me through how that breaks.
So if you are writing a generic wrapper function, say a function that logs a timestamp and then returns whatever some other underlying function returns,
Okay.
and you use a reference dropping operator to deduce the return type, your wrapper will always return a value. It forces a copy.
Even if the underlying function was intentionally trying to hand me back a reference to, like, a giant data structure?
Exactly. Your wrapper strips the reference, makes a heavy copy, and hands back a temporary value.
Wow. So variable declaration needs to actively drop references to be safe and intuitive for everyday coding.
Right.
But generic forwarding absolutely needs to preserve references, or else you ruin performance and break APIs that expose internal data.
They are entirely at odds, mutually exclusive requirements. You just can't have one tool do both.
So the C++11 committee had to split the job.
Yeah, they repurposed the legacy keyword auto to use template argument deduction rules. This means it explicitly drops top-level references and CV qualifiers, meaning const and volatile.
So auto guarantees you a clean, independent copy.
Exactly. Then they introduced decltype, which asks the compiler for the exact, unadulterated type of the expression, preserving references and const qualifiers perfectly.
Let me make sure I'm crystal clear on this. If I return auto from a generic wrapper function, I am always 100% of the time getting a copy.
Yes, you are.
That sounds like a terrifying trap for generic library developers because it silently degrades performance across every single call site.
It was a massive trap, and the standard recognized it. To bridge this exact gap, C++14 introduced a composite tool, decltype auto.
Ah.
This was designed specifically for cases where a function needs to deduce its return type from its return statement, but absolutely must preserve the exact references and qualifiers.
So it basically tells the compiler, deduce the type from the return expression, but use the strict decltype rulebook, not the reference-dropping auto rulebook.
You nailed it. That's exactly what it does.
Which fixes the generic wrapper problem.
Yeah.
But the sources point out this wasn't a free lunch. Using decltype auto introduced some pretty brutal SFINAE failure modes.
It did, and this is where the mechanics of compiler deduction get genuinely complex.
Let's ground this for a second.
Yeah.
For those catching up, SFINAE stands for substitution failure is not an error.
Right.
It's essentially a compiler rule that acts like a bouncer at a club checking IDs.
Mm.
If the compiler tries to substitute a type into a template signature and it doesn't fit, the bouncer just turns it away softly.
Exactly.
It says, hey, this template doesn't work, let's try the next overload, instead of just shutting down the whole compile process with a fatal error.
That is a fantastic way to visualize it. The problem with the decltype auto is that it bypasses the bouncer.
Wait, how?
Well, when a function's return type is declared as decltype auto, the compiler physically cannot know the return type just by looking at the function signature.
Because it has to look at the return statement itself.
Right. To figure out the type, the compiler is forced to step inside the function and fully instantiate the entire body to look at that return statement.
Oh, I see where this is going.
If a substitution error happens deep inside that body instantiation, it's no longer happening at the signature level. The bouncer isn't involved anymore. It is now a hard compile failure.
So it breaks generic library code that previously used soft substitution failures to gracefully compose different APIs.
Exactly. You trade the safety of signature-level checks for the convenience of exact return type deduction.
Wow. Okay, so auto drops references to keep our everyday variables simple, while decltype and decltype auto exist to preserve them for generic programming, bringing their own sharp edges.
Yep, that's the summary.
But what happens when the object auto captures isn't just a simple value, but a deferred calculation that relies on temporary variables. Because that brings us to what the sources call a silent catastrophic hazard.
Yes, the expression template hazard. This is where auto crosses the line from being a helpful reference-dropping tool to being a silent killer in your code base.
Here's where it gets really interesting. Let's talk about the Eigen Trap. I want to spend some time on this because it's a perfect example of mental models colliding with compiler reality.
It's a classic trap. Many high-performance scientific and mathematical libraries like Eigen or Blaze use a technique called expression templates.
Okay, what does that mean in practice?
If you multiply two giant matrices together, these libraries don't want to waste time computing the result immediately just in case you're going to chain more math onto it later.
Oh, so they evaluate lazily?
Right. When you multiply matrix A and matrix B, the library returns an intermediate expression object. It's essentially a lightweight recipe or a blueprint for the math. It is not the computed matrix itself.
So if I write auto result equals matrix A times matrix B, I am not getting a matrix filled with numbers. Auto is deducing the type of the blueprint. I'm capturing the recipe.
Exactly. Result now holds the deferred expression object. The actual heavy computation is deferred until you finally assign that blueprint to a concrete matrix type later in the code.
That sounds efficient, though.
It is, until you hit the fatal flaw. What if matrix A or matrix B were temporary objects? Say they were the immediate return values of some other function call.
Well, C++ rules dictate that temporaries are destroyed at the end of the statement. As soon as the semicolon hits, they're gone.
Yes. But your auto-result expression object is still sitting there, holding pointers or references back to where those temporaries used to be.
Oh, no.
You now possess an object completely full of dangling references. And the terrifying part, there is absolutely no compiler warning.
None. The compiler just lets you hold a map to a demolished building and says everything is fine.
Zero warnings. Because the syntax is totally valid C++A, the crash occurs much later in the program runtime.
When you actually try to use the matrix.
Right. At the point where the lazy evaluation is finally triggered, the library tries to execute the blueprint, accesses memory that has already been freed or overwritten, and causes a segmentation fault.
Or worse, it silently reads garbage data and corrupts your math without crashing.
Exactly. Which in scientific computing is a nightmare.
Okay, I have to push back here on a very famous, very widely adopted piece of C++ advice. Herb Sutter's got W number 94, strongly advocates for almost always auto, or AAA.
I knew we were going to get to this.
The fundamental idea is that developers should use auto by default for variable declarations on the left side of the equal sign. But if writing auto result equals matrix A times matrix B silently corrupts memory at runtime with zero warnings, recommending auto by default feels like wildly irresponsible advice.
It's a fiercely debated topic, and your reaction is exactly why.
How can the industry tell developers to almost always use a feature that actively arms a landmine in mathematical code?
Well, the defense for almost always auto is conceptually very strong for business logic and standard code bases.
How so?
If you use auto, it is physically impossible to declare an uninitialized variable. Writing auto x semicolon without assigning it a value simply won't compile. That alone wipes out entire classes of bugs.
Okay, that's fair.
Furthermore, AAA completely eliminates narrowing conversions. You will never accidentally cram a 64-bit integer into a 32-bit slot because auto scales to the exact size of the right-hand side,
Right.
and it avoids hidden temporary copies like when you accidentally bind a string literal to a standard string reference instead of a string view.
I acknowledge those benefits.
Yeah.
Guaranteed initialization is huge. Eliminating narrowing conversions is great, but memory corruption is an absolute showstopper.
It's definitely a massive risk.
If my team is using Eigen, or even the new C++20 range adapters, which also heavily rely on lazy evaluation, adopting AAA feels like playing Russian roulette with our memory safety just to save a few keystrokes or avoid an uninitialized integer.
And that tension right there is the synthesis of the debate in the community. AAA is completely correct, safe, and highly recommended in code bases that do not rely on expression template libraries.
Right.
It shines when developers have good IDE support to display the inferred types, but is a hazardous blanket recommendation for teams heavily invested in scientific computing, graphics programming, or lazy evaluation chains.
So what's the official stance?
The C++ standard itself does not take a position on this style guide, deliberately leaving the debate live. The takeaway for you, the listener, isn't never use auto.
It's know exactly which of your libraries defer computation before you mandate AAA across your entire team.
Exactly. Context is everything.
Fair enough. It's about knowing your tools. And that
It is.
limitation, the fact that auto captures the exact type of the expression, even if that type is a dangerous internal blueprint, forced the C++ language to evolve further.
It did. They didn't just stop at auto and decltype. They realized developers needed to capture types in more complex scenarios.
Let's look at the timeline. In C++14, the committee introduced generic lambdas. By simply dropping auto into a lambdas parameter list, the compiler automatically generated a templated call operator behind the scenes.
It was a huge ergonomic win. Before C++14, if you wanted a generic callback, you had to manually write out a whole struct with a templated operator parent. Generic lambdas made it incredibly succinct.
But, as you'd expect, dropping auto into parameter lists exposed a new limitation regarding nested types.
Right, the decltype inside lambda problem.
Walk us through how this breaks.
Imagine you have an auto parameter in your lambda, let's call it container, and inside the lambda body, you need to extract a nested type from it. For example, you need to know the value type of the container to declare a local variable.
Oh, okay. Simple enough.
But you can't just write container : value type because container is just a variable name. You have to query its type. So you use decltype container : value type.
Makes sense. I'm using decltype to ask the compiler what the type is so I can access its internal type def.
But remember our rulebook. Decltype perfectly preserves references.
Oh no.
Yep. If the lambda was called with a reference to a vector, decltype container evaluates to standard vector reference, a reference type.
And references don't have nested type.
Exactly. Here's a mechanical issue. References are just aliases or pointers under the hood. They do not possess class namespaces. You cannot ask a reference for its internal type defs. The code completely breaks.
Because the compiler tries to look inside a reference instead of the actual class.
Yeah.
So how did developers get around that?
They had to strip the reference manually using type traits like standard remove a reference inside the lambda, which made the code incredibly verbose again.
Which kind of defeats the purpose of the generic lambda being succinct.
Precisely. This friction made it clear that while auto parameters were nice, they weren't enough. The language needed a way to explicitly define template parameters on lambdas, which they finally added in C++20.
It's a constant game of whack-a-mole. Fixing one ergonomic issue exposes the limitations of the underlying type mechanics, which leads us to C++17.
Yes, C++17.
If C++14 was about generic lambdas, C++17 was about fundamentally rethinking how we instantiate class templates, primarily through CTAD class template argument deduction.
Right. Before C++17, if you wanted to create a simple pair, you couldn't just write standard pair p braces 1, 2.0. The compiler would refuse.
You explicitly had to write standard pair in comma double, or rely on a helper function like standard make pair to deduce the types for you.
CTAD changed the game by letting the compiler infer the class template parameters directly from the constructor arguments.
That sounds incredibly convenient.
Yeah.
But knowing how C++ deduction works so far, I'm guessing CTAD has its own distinct rulebook that developers need to memorize?
It absolutely does. CTAD introduces the concept of deduction guides. Because the compiler isn't magic, it needs a set of rules to translate constructor arguments into template parameters. Sometimes the compiler's default inference hits an ambiguity.
Let's use a real-world analogy or code example here. When did the compiler get confused?
Let's take standard vector. If you pass a single integer to a vector constructor, the compiler knows you want a vector of ints.
Right.
But what if you pass an existing standard vector of ints into the constructor of a new vector using CTAD? What is your intent?
Oh, I see. Do you want a brand new copy of the original vector, meaning the type is standard vector of int?
Right. Or are you trying to create a two-dimensional vector, a standard vector whose single element is the inner vector?
That is tricky. The syntax looks identical in both scenarios.
Right.
Standard vector v braces other vector. It's totally ambiguous whether I mean copy or wrap. How do deduction guides resolve that?
A deduction guide is basically a manual override provided by the library author. It tells the compiler, hey, when you see this specific ambiguous input, prioritize option A over option B.
Okay, so what does the standard library do?
For the standard library, the guide prioritizes copying. But if you're writing your own template classes, the default generated guides might make the wrong assumption, and you have to manually write out a custom deduction guide to steer the compiler toward wrapping instead of copying.
So CTAD isn't just auto for classes. It's an entirely parallel deduction system relying on author-provided guides to resolve structural ambiguities.
Yep.
Which brings us to the culmination of this 20-year journey, C++20 and constrained auto.
Proposal P1141R2. This feature allows developers to write abbreviated function templates.
All right, so instead of the verbose template type name T boilerplate, you can place concept-constrained placeholders anywhere. Auto is allowed in a function signature.
Exactly.
Okay, let me test my understanding here, because this is where a lot of senior developers get burned. If I write a function signature, like void process open parent sortable autoreference A, comma, sortable autoreference B,
Okay, tracking.
I am using the concept sortable to constrain both parameters. Does that mean the compiler forces parameter A and parameter B to be the exact same type?
No, it does not. And this is exactly where intuition fails. Abbreviated function templates use what is called the independent binding rule.
Independent binding.
Right. Each and every instance of auto in that signature, even if it is constrained by the exact same concept, generates a distinct, totally independent template parameter under the hood.
Wait, really? So parameter A could be a standard vector
Yeah.
and parameter B could be a standard set.
Yes.
And even though those are vastly different data structures, as long as they both happen to satisfy the sortable concept independently, the compiler just waves them through.
Precisely. It's like having two separate locks on a door that just happen to accept the same brand of key. They are not intrinsically linked.
Wow.
If your internal function logic genuinely requires both parameters to be the exact same type to safely compare or swap them, the abbreviated syntax is dangerous. You must revert to the explicit syntax. Template, sortable, T, void process, T reference A, T reference B.
That is a massive mental trap. Shipping code with independent binding when you actually intended joint binding produces subtly permissive APIs.
It really does.
You end up silently accepting cross-type function calls that your internal logic is absolutely not prepared to handle, which could lead to bizarre runtime errors or performance hits from implicit conversions.
It's a perfect example of why syntactic sugar requires deep semantic understanding.
Looking at this entire timeline, from the braces bug in C++11 to the SFINAE failures of decltype auto in C++14, the custom guides of CTAD in C++17, and the independent binding traps of C++20. A larger narrative emerges here about how the compiler actually views our code and the immense weight of backward compatibility.
It is a documented case study in the philosophy of language design.
Really is.
The committee repurposed the legacy T-word auto to avoid the immense friction of adding brand new keywords to the language, which could break existing code bases that use those words as variable names.
But that choice requires navigating every deployed use case.
Exactly. The cost of backward compatibility debt compounds over decades. They couldn't just invent a clean, perfect break. They had to painstakingly graft new deduction rules around the edges of the old ones.
So what does this all mean for you, the listener? The knowledge gap preventing you from fully mastering modern C++ was never about memorizing syntax.
Though the syntax is dangerously easy.
The real gap was not realizing that auto, decltype auto, CTAD, and constrained auto are basically 4 different compilers looking at your code with 4 completely different rulebooks.
Exactly. And the real danger is that on the screen, in your IDE, all 4 of those rulebooks use the exact same 4 letters, AUTO.
When you write plain auto, it drops references to keep variables isolated and safe. When you write decltype auto, it preserves exact references for generic forwarding, but risks hard SFINAE compile failures.
Right.
When you invoke CTAD, you're relying on constructor deduction guides that might need manual overriding to resolve copy versus wrap ambiguities. And when you use constrained auto in C++20, remember the independent binding rule. Every single auto is a totally separate template parameter, never a jointly bound one.
You now have a unified mental model to predict exactly what the compiler deduces in any context.
Armed with this model, how can you immediately protect your code base this week? We've pulled 3 specific actionable takeaways from the source material.
Action number 1. Audit one core file in your codebase for auto variables that capture results from Eigen, C++, +20 range adapters, or any mathematical library, uses lazy evaluation.
Good one.
If you find them, replace the auto with an explicit concrete type or append.eva to the expression to force the computation to finish before the result is captured. Do not let those blueprint objects dangle.
Action number 2. Migrate one class template construction site in your code from the old C++11 standard make pair or standard make tuple style over to C++17 CTAD. Just let the constructor do the deduction work.
And if the default inference gives you the wrong type, like making a copy when you wanted a wrapper, take the time to write an explicit custom deduction guide.
Exactly. And action number 3, especially for teams actively migrating to C++20. Rewrite one function template using the abbreviated syntax, a concept followed by an autoparameter.
Yes, deliberately write a failing test case to verify that the constraint correctly rejects the types it's supposed to reject. Confirm for yourself that the independent binding rule is actually doing what you intend it to do and not leaving your API wide open to mismatched types.
Which of these three actions are you doing first? And seriously, if you or your team have already fallen into the eigenmemory corruption trap, we want to hear about it. There is zero shame in getting caught by a silent compiler hazard that hides behind such an innocent-looking keyword.
It happens to the absolute best of us. As we wrap up today's deep dive, I want to leave you with a broader philosophical